Okay, good evening everyone. Welcome to the 16th Andrew Chamblin Memorial Lecture. So if you don't know who I am, I'm Harvey Rial. I'm a Professor of Theoretical Physics here in the Department of Applied Maths and Theoretical Physics at Cambridge University. So before I introduce today's speaker, I'd like to tell you a little bit about Andrew Chamblin and the history of this lecture series. So Andrew was born in Lubbock, Texas, and brought up in nearby Amarillo. After a brilliant undergraduate career at Rice University, he moved to the UK to study for a year in Oxford, where he worked on twistor theory with Roger Penrose. He then moved here to Cambridge to study for a PhD under the supervision of Gary Gibbons and Stephen Hawking. He was subsequently elected to a junior research fellowship at Pembroke College, and then after that he held postdoctoral positions at several institutions before becoming an assistant professor at the University of Louisville in Kentucky. He produced many influential papers on general relativity and quantum gravity, including one which now has over 1,000 citations. Sadly, Andrew died unexpectedly in 2006 at the age of just 36. Following his death, his friends and family established this lecture series in his memory. So the first Andrew Chamblin lecture was delivered by Stephen Hawking, and following him there were many other very distinguished speakers, and you can find recordings of some of the previous talks on our website. So now to today's talk. So practical point, if you'd like to ask the speaker a question, then there'll be an opportunity to do so at the end if we have time. There are people watching this on Zoom, I hope. We're having a few technical problems, but I think we sorted them out. If you're on Zoom and want to ask a question, you can do so using the chat function. My colleague George Santos is monitoring that, and he will pass questions on to me. Okay, so with the administrative arrangements out of the way, I'd now like to introduce our speaker. So Robert Wald earned his PhD from Princeton in 1972 under the supervision of John Wheeler. He joined the faculty of the University of Chicago in 1976, where he is now Charles H. Swift Distinguished Service Professor in the Department of Physics and the Enrico Fermi Institute. In his research, Bob has made numerous important contributions to the study of general relativity, to black hole thermodynamics, and to quantum field theory in curved spacetime. He's also written several highly regarded textbooks, including a book on general relativity, which, although nearly 40 years old, is still regarded by many, including me, as the best textbook on the subject. So Bob's research achievements were recognized by election to the National Academy of Sciences in 2001, and the award of the Einstein Prize by the American Physical Society in 2017. So please join me in welcoming Bob to deliver the Andrew Chamblin lecture this evening.
Okay, well, thank you very much for the introduction. It sounds to me like the microphone is working. I hope people can hear me, and all technical issues are taken care of. So I want to tell you in the next hour about black holes, thermodynamics, and a little bit about the information loss issue. And let me begin by telling you about what a black hole is. So by definition, a black hole is simply a region where gravity is so strong that nothing or anything that enters that region is then unable to escape from it. So nothing can escape from a black hole by definition, and that nothing includes light. So black holes are indeed black, since no light is going to be coming from them. Now, black holes are normally regarded as quite exotic objects, predicted as they are by general relativity, but a lot of the basic idea, not all of it I'll explain, goes back quite a bit further to Mitchell here, and a bit later than that, Laplace. What these authors did, using the 100-year-old or so then Newtonian theory of gravity, general relativity is now 100 years old, is in effect do a calculation of the escape velocity from the surface of a star or planet. I mean, you're very familiar with the fact that if you throw something up, it comes down again, but that's only true if you throw it up without enough velocity. If you throw it up from the surface of the Earth fast enough, faster than this escape velocity, it won't return to Earth. It will keep on going forever. And what these authors noticed is if the radius of the body was related to its mass by this relation, we would now say the radius of the body is smaller than its Schwarzschild radius, defined in terms of the mass by this formula where g is Newton's gravitational constant and c is the speed of light, then the escape velocity would be larger than the velocity of light. It was already known, and the velocity of light indeed was measured by the time of these authors. It was known that light traveled at a finite speed. So these authors predicted light would not be able to escape from the surface of a star or planet whose radius is less than its Schwarzschild radius. Now, if you calculate what this is for the sun, you'll see that the Schwarzschild radius is only 3 kilometers. The sun is much bigger than that, so there's no problem with light escaping from the surface of the sun. The Schwarzschild radius of the Earth is about that big, a few centimeters. Earth is a lot bigger than that. But if you had stars that were much more massive, they could be within their Schwarzschild radius without being at a ridiculously high density. They didn't know the mass of stars, of course, in that day. So they predicted that there ought to be stars, dark stars, that you wouldn't be able to see because the light from the surface of those stars wouldn't be able to escape. Well, there's one major difference between that picture and the picture that we get in general relativity. Again, if a body is smaller than its Schwarzschild radius, exactly the same formula that Mitchell and Laplace have derived, light will, as they predicted in a sense, be pulled back in. But the key thing in special and general relativity is nothing can travel faster than light. So in effect, if light is going to be pulled back in, everything is going to be pulled back in, including the body itself. The surface of the body can't remain in equilibrium. It's got to be pulled in. And the statement in general relativity is a body that is this compacted simply can't exist in equilibrium. It will, in fact, have to undergo complete gravitational collapse to a singularity. I will elucidate this in a few minutes, considerably. Now, there is a lot of evidence, although this evidence is mostly indirect arguments that are looking at the consistency of the idea, but there is considerable evidence that the endpoint of collapse is in fact a black hole, that the so-called cosmic censorship conjecture is true. We know much more rigorously that some sort of singularity will have to result from gravitational collapse, but there is very good reason to believe that those singularities are always hidden within black holes. That is, there is always a region of no escape around the singularity. Again, I will elucidate that further. So that the end product of what happens to a body that gets compacted within its Schwarzschild radius is always a black hole, a region of no escape. So again, I will illustrate that, but before I do, I want to talk briefly about black holes in our actual universe. So most of this talk will be on the universe of theoretical ideas and the nature of black holes and so on, but black holes really exist as physical, astrophysical objects in our universe. And so I want to at least say a few words about that and then return to the theory of black holes. So there are actually three basic, fairly distinct processes by which black holes, well, are certainly expected to have formed in our universe in the first two. This last process is completely hypothetical, but it may have occurred. So the first process, and the one that can be best understood and studied, is the complete gravitational collapse of a star. Now, stars like our sun are not anywhere near forming black holes at the present time. Their radius is much too large, their size is much too large, but they're being held up by pressure caused by high temperatures, and that's being maintained by thermonuclear reactions. Eventually, the sun and all other stars are going to run out of thermonuclear fuel. And at that point, they're going to have to be held up by some means other than high temperatures in order to prevent them from just collapsing under their own self-gravitation, under their own weight. Well, there are such forces in nature, and a very prominent one is so-called electron degeneracy pressure. It's really a quantum mechanical effect resulting from electrons it costing a lot of energy to squeeze electrons together because of the Pauli exclusion principle. Two electrons can't occupy the same state. But as Chandrasekhar, a very young graduate student here at Cambridge in the early 1930s showed, that force can hold a body up only if it's less than about 1.4 solar masses. So the sun will be able to end not as a black hole, but as a so-called white dwarf star that's supported by electron degeneracy pressure after it's used up its thermonuclear fuel. If you have heavier bodies than that, they can still save themselves against gravitational collapse by a similar neutron degeneracy pressure and nuclear forces. Bodies that are held up in that manner, again not requiring high temperatures and pressures generated by high temperatures, are known as neutron stars. They're commonly observed as pulsars, but they can't be supported unless their mass is less than about 2 to 3 solar masses. This is a bit uncertain because we don't know the nuclear forces that well, but it's somewhere in this range. But if the mass of a star is bigger than 3 solar masses and it doesn't shed mass in the course of evolution or in a supernova explosion to get below this sort of limit, then it will have to collapse to a black hole. So one expects that there are many black holes in the universe that were created in this manner. They would have a mass range no bigger than between 2 solar masses, because they wouldn't collapse otherwise. And because of various instabilities, it's unlikely that we would have the stars around with mass greater than 300 solar masses at a stage where they could collapse to a black hole. A second process is the collapse of the central region of a galaxy or a dense star cluster. There are various scenarios that people have proposed for how this could happen, but it's really not very clear how this all, it's certainly not obvious how this works, and all of these scenarios are tending to kind of push the limits on what might be possible, mainly because we know these form extremely early. Quasars, quasi-stellar radio sources, as discovered in the 1960s, are believed to be powered by black holes, and we are finding quasars at higher and higher redshifts, meaning they formed black holes of this size formed in the very early universe, and again, it's really not obvious how this happens, but it clearly did. We expect and observe black holes in this kind of mass range, 100,000 to 10 billion or so solar masses that were formed in this way. Finally, there's a distinct process of black holes that could have been formed in the very early universe. There's no reason to expect that any were by this process, but this is quite interesting because this gives a mass range of anything. So to explain what I mean by that and how this manages to give a mass range of anything, if any black holes indeed were produced in this manner, suppose we decided we want to make the Earth into a black hole. As I say, it would be a black hole of about that size. Well, the problem is that we would have to find some non-gravitational means to compress the Earth down to, let's say, this size. I mean, we don't know the properties of matter at these densities, so that's a guess. But once it got down to about this size, the self-gravity would be so small, so strong that it would go the rest of the way and collapse to a black hole. But it is a real problem to imagine, a difficulty to imagine a process that would, non-gravitational process that would crush the Earth down to, let's say, this size. However, if we go back early enough in the evolution of the universe, we can go back to a time when the average density in the universe was what the Earth would be if it were this size. And if the conditions in the early universe were such that the density in a region of this size was, let's say, twice the average of the densities elsewhere, that region might collapse and form an Earth-sized black hole. So you could get anything in this range, but there's no reason to believe that the density and homogeneities were so large, and there's no observational evidence for black holes produced in this manner. But there is a tremendous amount of observational evidence in our universe for black holes. For the stellar-sized black holes, there are at least about 20 known binary systems that contain a compact object whose mass is greater than 3 solar masses. So there's no plausible explanation for what that component could be other than a black hole. For the galactic-sized black holes, almost all nearby galaxies, 30, 40 of them most nearby, show clear evidence of some very massive object at their center, which again, plausibly could only be a black hole. Our galaxy, our own galaxy, is definitely one of the best and best studied examples of this, and there is a mass concentration at the center of our galaxy that is no bigger than about 1,000 Schwarzschild of its the Schwarzschild radii of this mass, there's really no plausible thing this thing could be other than a black hole. And indeed, these observations won the Nobel Prize a couple of years ago. I think Andrew Getz was one of the Chamblin lecturers. But the most dramatic evidence for black holes has come more recently than some of these things I've told you. One of the two really quite striking and dramatic major pieces of evidence for black holes comes from the ability of LIGO, and now Virgo as well, to detect gravitational wave signals. And if you have two black holes that are in orbit around each other, they will emit gravitational radiation. Their orbit will lose energy and decay in this manner. The orbital radius will get smaller. Eventually, the black holes will merge and settle down to some single black hole. In this process, they will emit a characteristic waveform of gravitational radiation. And amazingly, that is exactly the sort of thing seen in the gravitational wave detectors beginning in 2015. And indeed, there are now about 90 events of detection of gravitational waves of this sort, almost all of which are the mergers of two black holes. There are a couple of cases of neutron stars instead of black holes, which also will emit signals of this nature. But it's really quite remarkable evidence for the existence of black holes and a remarkable tool for studying the populations of black holes. The other relatively recent dramatic piece of evidence is the Event Horizon Telescope and their image of a black hole. This is the black hole in the galaxy M87. There's a more recent image this year, though not of as good quality and reliability, of the black hole in the center of our galaxy. But I don't think I have to say that much more to assert the fact that this image very much confirms the fact or the presence of a black hole. I mean, it was already known from other arguments and observations that there must be a very massive black hole at the center of M87, but this really confirms the existence of a black hole of about 6 billion or so solar masses at the center of M87. Okay, but this, of course, is not really a picture of a black hole. This is a picture of the matter that is around the black hole, outside the black hole. We're not going to see anything once it goes into the black hole. So this is matter accreting onto a black hole, and we're seeing that matter. And indeed, this is a remarkable tool for studying the physics of that matter. But this talk, I'm interested in black holes, so let's see what a black hole would look like without cluttering it up with all this matter around it that we're not interested in. So here is an exact picture of a black hole, right? The black hole is right there. So this is what a black hole really looks like, not with all that junk around it to distract you. Okay, so we're not going to learn a lot about black holes by looking at pictures of black holes, but we really, if we want to understand black holes, there is, well, kind of picture, I mean a depiction of them that I think is really essential and needed for understanding their nature. And I want to take a bit of time to explain this to you. So what I'm drawing here is what's called a space-time diagram. And this is a space-time diagram depicting the gravitational collapse of a body to a black hole. So each point on this diagram is supposed to represent what one calls an event in space-time, a point of space at an instant of time, like the snapping of my fingers is kind of representative of an event. The rules for the conventions for drawing the space-time diagram are that forward in time is upward in the diagram and the spatial directions are represented horizontally. So if you want to read a space-time diagram, you should start at the bottom of the page and go forward, and that's telling you what's happening as time progresses with respect to whatever you're looking at. Now, there's a major problem in drawing space-time diagrams, well, two major problems. One is that the screen is two-dimensional, but space-time is four-dimensional, one dimension for time and 3 dimensions for space, so you've got to suppress at least one spatial dimension in any space-time diagram. The other problem is that general relativity represents gravity as curvature in space-time, so space-time isn't flat, whereas this screen is a flat geometry. So much like a wall map of the curved surface of the Earth, there are also necessarily going to be some distortions in the way things are represented in any gravitational, non-trivially gravitational space-time diagram where the curvature of space-time is playing a role. But nevertheless, let's look at this space-time diagram. So this sort of semicircle that I have down here, I've suppressed a spatial, it's really a circle. I'm using perspective to get 2 spatial dimensions in. But what that really is representing is a 2-dimensional spherical surface of a star back here at early times. And what happens to this star is its radius shrinks. It gets smaller and smaller. It keeps getting smaller and smaller, and eventually the radius collapses to 0. And as it does so, it creates a space-time singularity. I've tried to draw some jaggedy, scary-looking thing here to represent the singularity. And that's what happens in gravitational collapse. All of the matter goes into this space-time singularity. So where is the black hole, and how can you tell that there's a black hole? Well, the only way you can tell that in this diagram is by my drawing in these so-called light cones. So if I emitted, put this down for a second so I can use both hands. If you imagine that I emitted a flash of light right at the event where I snap my fingers, that light would travel out at the speed of light in a spherical manner. If I represent that, but of course the light is going forward in time as well as expanding in space. So if I represented that on a space-time diagram, the trajectory of the light rays, these spherically expanding light rays, would look like a cone, expanding out at the speed of light, but going forward in time. The light cone that I've drawn out here, safely far from gravitational collapse, looks sort of like the kind of light cone one might draw in a special relativity space-time diagram. And if I'm an observer here, well, the key thing is I can't move faster than light, so I always have to move within the light cone. But if I want to get back out far away, I can do that. The speed of light doesn't prevent me from doing that. However, near the singularity, these light cones are all tipped over, pointing toward the singularity. And if I happen to be an unfortunate observer over here, just the fact that I can't travel faster than light will force me to fall into the singularity. And there's nothing, no rocket ship, anything else will help me because rocket ships can't make me go travel faster than light. So this event is in the black hole. In fact, all of these events are within the black hole. The boundary of the black hole, which is referred to as the event horizon, given by the same formula that Mitchell and Laplace had derived, that has the property that there's sort of one light ray that would not fall into the singularity, but also not go out to infinity, and everything else would fall in. Once I'm outside of this event horizon, though, then I can make it to infinity. If I'm inside the event horizon, or in other words, if I'm inside the black hole, then I'm going to have to fall into the singularity no matter what I do. So this is the basic picture of what the nature of a black hole in general relativity. Now, as I said, there's distortion due to representing a curved geometry on a flat geometry, a little like, not that closely analogous, but somewhat analogous to, looking at Antarctica on a wall map. Some things are really a bit distorted in that picture. So it's actually, since I'm mostly interested in the black hole and, well, for this purpose, illustrating the nature of the singularity, it's very useful to redraw exactly the same space-time diagram, but where I straighten out the light cones so that they're in this new representation, they're all at, well, 45 degrees, much like this one. So I'm redrawing the interior of the black hole in particular to do that. Now, that gets very confusing to do if I try to represent angles and represent a second, 2 dimensions of space in that way. So I'm going to, the diagram I just showed you, which I'm going to go back to, is just going to draw time going forward and only going to draw the radial distance from the center of spherical symmetry that I'm assuming here in these diagrams, and I'll suppress the angles. And this is what that diagram looks like if I straighten out the light cones in this manner. So now everybody can move at an angle. It's possible for an observer to do anything, any motion with a powerful enough rocket ship, as long as they stay within these 2 45-degree lines that I've drawn here. And outside in this region, you can make it out as far as you want from this black hole region, but the singularity is much more properly represented now in this diagram as a kind of end of time, not kind of a point of space that you're, that exists for all time, which is kind of how it's being drawn here, but here it's very misrepresented because of these tipping over of, you have to take the tipping over of the light cones into account. And if you straighten them out, then you see the singularity more properly as being a kind of end of time. So if somebody has the misfortune to be here, just the fact that they have to go forward in time, they're going to fall into the singularity. What this depicts much better than the other picture is that the curvatures only get very strong as you get very near the singularity. When we really get near the singularity, we wouldn't expect this classical general relativity description that I'm giving to be valid. We'd expect the theory to break down. But it's only going to break, or it only should break down in a little neighborhood of this singularity. That should not affect anything going on outside the black hole or a bit of a ways inside the black hole, because that's all in the past of the singularity, or space-like separated from the singularity, but it's not something that should get any causal effect from whatever breakdown we have in the, of the theory. So again, this diagram is intended to illustrate that the singularity is kind of an end of time for all observers who have the misfortune to go into the black hole. It also more properly shows the event horizon as, generated by light rays. This is at the edge of a light cone here are light rays, and those generate this event horizon. Okay, well, let me move on now to a discussion of thermodynamics of black holes. So this is really, a completely unexpected and, I would say rather mind-blowing analogy that turns out not to be just an analogy, but deep physics. So beginning in the early 70s, it was recognized that there are some analogous features between black holes and thermodynamics. For one thing, in ordinary thermodynamics, if you fill a box with gas or something and wait a while, it will settle into a thermal equilibrium state that's characterized by just a handful of state parameters. Similarly, it turns out, very non-trivial mathematical theorems, but that, well, one would expect, first as an expectation, one would expect that if you formed a black hole by gravitational collapse, it would settle down to some stationary final state. Very non-trivial theorems proved in the 60s and 70s show that, in fact, that state is uniquely described by just a few state parameters: mass, angular momentum, and electric charge. Now there's a zeroth law of thermodynamics that says, well, if you have a body that locally reaches thermal equilibrium, you can introduce a notion of temperature, and for global thermal equilibrium, that temperature has to be uniform over the entire body. There's a similar law that says that for a stationary black hole, you can define a notion of surface gravity, and that surface gravity has to be constant over the whole horizon of the black hole. So we're taught in elementary physics that the surface gravity of the Earth is the acceleration that an object dropped at the surface of the Earth would undergo due to gravity. Now, in general relativity, that's a bit reversed. because a freely falling object like this one is viewed as not accelerating, but you can define the surface gravity as the force that you would have to exert on a unit mass body to keep it stationary. By that definition, the surface gravity of a black hole is infinite. You'd need infinite force to hold something stationary as it approaches the event horizon. But if you redefine the surface gravity by multiplying that acceleration by the so-called redshift factor, the factor that the frequency of a photon will decrease as it climbs away from a black hole, that product approaches a finite limit, and it's a theorem in general relativity that the surface gravity has to be constant over the surface of a stationary black hole. Well, that's not enormously, what I've told you so far is not enormously impressive as an analogy between black holes and thermodynamics, so on. But now it gets a bit more interesting because there is a first law of black hole mechanics that's closely analogous to the first law of thermodynamics. So in thermodynamics, there is an entropy quantity that can be associated to a body that's, you know, in a thermal equilibrium state, it will be a function of the state parameters. And the first law of thermodynamics relates if you perturb a system in equilibrium, it relates the first order change in the entropy to the first order change in the state parameters. For those of you who've taken any physics course, this sort of formula should look familiar, but there's an exactly analogous formula for black holes in general relativity that is now introducing the area of the event horizon of a black hole into this equation. And this formula says that if you perturb a black hole, the change in the area of the event horizon is going to be related to the change in the other state parameters by a formula of this sort. Well, I've introduced kind of angular velocity of a horizon and potential of horizon here. That's not important, and nor is it important the form of the work terms here. It's just that these terms have a similar character of variation of state parameter to that I want you to see. So that's rather striking, but what's really striking is the second law of thermodynamics, which says if you have some isolated system, which now may be far from thermal equilibrium, the entropy quantity never decreases. Whatever happens to the system, the entropy at late times is always at least as big as it was initially. And that is remarkably analogous to Hawking's area theorem in classical general relativity, which says that the surface area of the event horizon of a black hole similarly never decreases. Do anything you want to the black hole, its area will, at the end of the process, always be at least as big as it was initially. So there are not that many laws of physics that have inequalities in terms of behavior and time. So that is really rather striking, and when put together, it's all rather striking. And if we look at what the analogous quantities are in these formulas, and for that matter in the zeroth law as well, well, temperature and surface gravity are coming in the same way, energy and mass are coming in the same way. Area and entropy, most importantly over here, are coming in the same way. But in relativity theory, mass and energy are really the same quantity. So there's a hint already that this may be more than just some analogy. When Bardeen and Carter and Hawking in 1973 first elucidated this analogy in full, they were all convinced that this was merely an analogy, and mainly because the temperature of a black hole is clearly absolute zero. Nothing can, it doesn't emit anything by definition. So how could surface gravity really be physically the same thing as temperature? Well, that then a year or so later, there was a rather dramatic reversal in that, and I would say one of the, probably the most remarkable development that occurred in my, physics career, is that if you look at quantum processes around a black hole, there will be particle creation effects, and there will be particles created outside of the black hole that can propagate out to a distant observer. Things inside the black hole are going to stay inside the black hole, so that's not going to do anything. And truly, amazingly, Hawking showed that a black hole radiates, in effect, again, nothing is coming out of the black hole, but there's particle creation occurring in the neighborhood of a black hole for which particles propagate out to infinity at a temperature that's given just by the surface gravity. Now, this is a very tiny temperature for a solar mass black hole, and even tinier for a galactic center of galaxy mass black hole. For a solar mass black hole, it's only 10 to the -7th degrees above absolute zero. But as a matter of principle, this is incredibly important. And there's a further important ramification of this that Hawking also noted at the same time he discovered this effect, which is because of the thermal radiation that a black hole is emitting, it should lose mass. And because it's thermal radiation, one can go to textbook formulas for the rate at which energy is emitted, and that's proportional to surface area times temperature to the 4th. The surface area scales as mass squared, but the temperature scales inversely with the mass. So that means the smaller the mass of the black hole, the more it radiates. But that implies that if a black hole were left by itself, just radiating out into empty space, it would completely lose all of its mass in a finite amount of time. That finite amount of time is pretty darn long for a solar mass black hole. It's barely radiating at all at this stage, and it's only slowly going to lose mass and get hotter. But if you had a primordial black hole of mass the size of Mount Everest, mass of Mount Everest, I should say, size would be about the size of an atomic nucleus. So that's what the Schwarzschild radius of Mount Everest is roughly. That would be, if that was created in the early universe, that would be evaporating now. So that's another very striking prediction of the Hawking radiation. So that leads to this modification of the picture of a black hole that I was drawing. I mean, there's a lot of other things that this leads to, which I will be talking about. Again, this is not, you can't see this easily on this diagram, but here this part of the diagram is just what I drew before of a star collapsing, forming a singularity that's a kind of end of time, as I described. So that's as before, but now, due to Hawking radiation, although you have to take my word for it, you can't easily read this from the diagram, the event horizon is shrinking in radius. And the radius is getting smaller and smaller, and I've shown it here now disappearing to 0 size. The black hole has now completely evaporated, disappeared from the universe, and that's the new picture of a black hole. Of course, this would only be for an isolated black hole that, doesn't have more matter falling into it, but the fact that in principle this should happen is really very striking and, well, very significant. So if we return to the analogous quantities, now we see that the temperature of a black hole in a very real sense is not absolute zero, but it is in fact the surface gravity up to numerical factors and constants of nature, which I guess set equal to 1, and many of them in this formula. I'll put them back in the next slide. I had forgotten I had done it in this slide. But the key point is the surface gravity really is up to numerical constants, the physical temperature of a black hole. So that suggests very strongly that the area of a black hole must represent its entropy. I mean, a rather kind of crazy idea on the face of it. So what is the evidence that that's true? Well, there's very good reason to think that that's true because, in fact, I already mentioned the second law of thermodynamics. I also mentioned the area theorem of Hawking, but there's actually a serious problem with both of these laws. So what's the problem with the second law of thermodynamics? That's one of the most robust laws in physics. Well, the problem with that is if you have a black hole present, you can throw matter into a black hole, and voila, the entropy of matter outside black holes has decreased. Well, you might say, let's count the entropy of the matter that went into the black hole, but then this is a bookkeeping law, not a law of physics, because you can't see anything about that matter if you're outside the black hole, and even if you run in, let yourself fall in, you still won't catch up to it. It'll disappear in the singularity before you get there. So if we only count matter outside the black hole, we can violate the second law quite easily. On the other hand, Hawking's area theorem has a hypothesis. It is a theorem, but part of the hypothesis is that only positive energy is going into the black hole. In the quantum particle creation process, in fact, there is a flux of negative energy going into the black hole. That's how it decreases its mass. And the area theorem is violated. So what do we do about this? Well, Bekenstein came up with a brilliant idea even before Hawking's particle creation calculation, when there really wasn't very much justification for believing this. But he suggested, let's add the entropy of matter outside black holes to the area of black holes. And now I've put in the fundamental constant speed of light, Newton's gravitational constant, and h bar into this formula. And now, now we get a quantity that quite plausibly never decreases. Why? Well, we could decrease the entropy of matter outside black holes by throwing this ordinary matter into a black hole, but that will increase the area of a black hole, and it doesn't have, with these, in ordinary units, with these constants of nature, it doesn't have to increase very much to completely overwhelm the loss of entropy. On the other hand, in the Hawking particle creation process, you lose area, but you do so while you're doing so, you're spewing out a thermal distribution of particles that has a lot of entropy. And indeed, if you carefully look at these processes, and there are other arguments as well, it appears that what's referred to as the generalized second law of thermodynamics is true, that this generalized entropy, that this is a correct law that replaces the ordinary second law for S and the area theorem for A. But if this is correct, as it definitely seems to be, what's the interpretation? Well, the natural interpretation is this is really the total entropy. This is the contribution from ordinary matter outside black holes. This is the contribution from the black hole, or black holes. So this apparent validity of the generalized second law very strongly suggests that this is the physical entropy of a black hole. That doesn't kind of answer all questions. I think there's still quite a number of mysteries to explore on this. In ordinary thermodynamics, one understands the entropy of a body as counting, representing the number of possible states of that body that have the same macroscopic qualities as the state we're talking about. And it would be natural to imagine that black hole entropy is counting the states of a black hole in quantum gravity. We don't have a quantum theory of gravity which is capable of, answering questions of, what does an observer see? What are the properties of all the properties of a quantum black hole, and so on. So, this is really a very important clue as to the nature of black holes in quantum gravity. But if the entropy is counting states, it's really not clear certainly not clear to me where these states reside and how one understands exactly what states it's counting. But as I just indicated, I think this formula for the entropy of a black hole that I have here, the Bekenstein-Hawking formula for entropy, is probably the biggest clue we have to understanding the nature of black holes in a fully quantum description of gravity. Okay, well, I am well over time in terms of where I wanted to be, and I'm almost over time in terms of the lecture. I wanted to say a number of things about the information loss issue. So let me try saying a few things, and I'll keep my eye on Harvey in terms of when he starts standing up and the smile on his face disappears. and so on. But quantum theory is quite strange in its own right. In classical theory, you can specify the state of a system by just giving the exact values of an appropriately complete set of observables. In quantum theory, you have a precise description of a state, but it's specified as an abstract object in an abstract Hilbert space, where you then have well-defined rules for calculating probabilities of observing things, but the observables don't have definite values. The amazing thing about quantum theory is it does seem to describe nature, as we've found over 100 years or so of testing the theory. The weirder things occur when you have subsystems. The Hilbert space of a system consisting of subsystems is just this product of Hilbert spaces. I'm not going to go into mathematical detail on this. And product states are, no weirder than, quantum mechanics itself. A state of this sort just has the properties of psi2 for the second system, the properties of psi1 for the first system. The weird thing is that you can have superpositions of these states, and that creates states where there are correlations between the probabilities of what you observe in the first system and what you observe in the second system. And that creates the weirdest features that one sees in quantum mechanics. So if a state of one system is entangled with another, it's referred to as a mixed state. If it's in this sort of product state, the subsystem, let's say this second subsystem, is referred to as being in a pure state. Now, entanglement is an absolutely ubiquitous property of quantum field theory, and at short distances, quantum fields are always very strongly entangled with themselves. This has to do very much with the black hole particle creation process, because there's going to be entanglement of quantum field observables inside and outside the black hole. And indeed, the Hawking radiation is very closely related to this short distance entanglement. The short distance entanglement is not normally something we'll notice, but if it's between the outside and inside of the black hole, stuff outside can propagate to infinity, stuff inside will propagate into the black hole, and it now becomes over macroscopic distances. So in this diagram that I have of an evaporating black hole, one can see the issue. We can imagine that we've started with some ordinary pure state of matter in the quantum theory down here at this initial time before the collapse has taken place. When we have a black hole, we are going to get correlations, entanglement between the quantum field outside the black hole and inside the black hole. That's intimately part of the Hawking radiation, but we could produce such entanglement by throwing entangled matter into a black hole anyway. That's not too shocking, but what is a huge surprise, shock possibly, is if the black hole evaporates completely. Well, this stuff here, this subsystem here, is still, in some sense, entangled with what was in the black hole, but there's no longer any black hole. And we end up then in this picture with evolution from a pure state to a mixed state. So if I had considerably more time, I would talk about, but I don't, I would talk much more about what could be wrong with this picture. Maybe you don't actually form a black hole. There are some ideas in that regard. Maybe this picture that I'm describing of the Hawking radiation and its entanglement goes drastically wrong during this long phase of evaporation. The firewalls idea and the recent talk about wormhole tunneling kind of ideas fit in that category. Maybe the black hole doesn't completely evaporate, that's the remnants idea, or maybe there isn't really a singularity here and maybe everything comes out in a final burst. So the remnants don't really help anything if you can't access them, and there are thermodynamic arguments again if you can. Getting everything out in a final burst is highly problematic. These ideas, I would have said much more about it, are really radical ideas, I would claim, that say that physics is very different from what you would expect from classical general relativity and quantum field theory in a regime which can be very low curvature, you're nowhere near, this singularity, and so on. But I don't have time to talk about that. If I did have time, and you can see I have some slides on all this, and I can answer questions about it. I would also, had I had another 10 minutes, talked about arguments as to why, as best as I can reconstruct, people are very unhappy with the idea that you might get loss of information and pure states evolving to mixed states. The majority view definitely seems to be very unhappy with that. I'm more in the minority of not being perturbed by that idea at all. I would have explained that we're losing information to infinity all the time, and ending up in a mixed state. If there were windows in this room, we have, might have atoms emitting photons, but being in an entangled state with those photons. If those photons were to make it out of this hypothetical window that I'm pointing to, make it through the clouds, tonight you could do that in Cambridge, most nights I think not, make it beyond the Earth's atmosphere, then it's probably not going to get encountered with anything else. We are left in a mixed state because we're entangled with that photon, and we can't catch up to that photon or do anything about it. There have been arguments about problems with energy and momentum conservation, but those are making assumptions not of that, that would not be really appropriate for a black hole. And then there's a major argument that I wouldn't have had a lot to say about anyway, having to do with arguments against information loss arising from the so-called ADS-CFT conjecture. And my discomfort with these arguments really has to do with the fact that the kind of dictionary between the CFT and quantum gravity has just not been spelled out with enough precision to make this into some, argument that I would feel at least comfortable and confident in. And that's assuming we believe in the validity of the conjecture, and in particular, I don't see why, for example, the late time CFT state can't encode some of this early time or all of this early time information that in the bulk propagated into the black hole and is not accessible at late times in the bulk, but why can't it still be accessible in the CFT? In any case, I don't personally see any compelling reasons against information loss, and I don't see any compelling, other scenarios, that don't have serious problems of their own. I don't think that everyone by any means would agree with me on this statement, but in my conclusion, I think there really will be or is universal agreement. My conclusion is that the study of black holes has really led to a mind-blowing connection between gravity, quantum theory, and thermodynamics. And it's definitely my hope and expectation that we haven't seen the end of this. We're going to get additional fundamental insights from further investigation of black holes and its relationship to thermodynamics and quantum theory. So, thank you very much.
Thank you very much, Bob. That was a beautiful talk. I think in view of the time, we don't have a great deal of time for questions, but maybe one quick question, either from someone in the room or someone remotely on Zoom. Yes.
How was quantum entanglement discovered? Can it be proved that...
I'm sorry, repeat again, I couldn't quite.
How was quantum entanglement discovered, and can it be proved with any experiments?
Yeah, so, quantum entanglement was, noticed early on. That it is one of the major things that bothered Einstein and why he wasn't accepting of quantum theory. There is a famous paper of Einstein, Rosen, and Podolsky from the late 1930s, which is basically arguing that quantum mechanics can't be correct or can't be complete because of phenomena that you would get with entanglement that don't make any sense. That appear to violate causality, although when you look at it, you really can't send a signal. By around 1960, Bell refined these sort of arguments to show that there really was an incompatibility between these entanglement predictions of quantum mechanics and the kind of probability distributions that you could produce classically from just not knowing the definite state of your two subsystems. And then subsequently, experiments were done that showed that indeed the correlations that you got in measurements of appropriate subsystems were exactly in accord with quantum mechanics, but incompatible with classical probability distributions.
So, thank you for that question. So, I think probably have to stop now. So let's thank Bob again for giving